So now that we know how to compute derivatives, we're going to explore this idea further. Just remember that when we compute derivatives, what we're computing is a rate of change. So when we compute the partial derivative of z with respect to x and the partial derivative of z with respect to y, we're finding specific rates of change with respect to x and y. So if we look at this first bullet point, it describes a partial derivative as a rate of change on our surface z in the direction parallel to the x-axis and the y-axis. However, and this is the same concept we had when we looked at limits, there are infinitely many paths or directions to a point. So let me draw a graph and describe what I mean by directions parallel to the x and the y-axis. Let's just say that we have some point AB. So this would correspond to some B value on the y-axis, some A value on the x-axis. And let's just say that this corresponds to some surface Z. So I'll just draw some generic surface. If we look at that point AB, it's going to correspond to some point on our surface. So when we compute the derivative with respect to x, we're holding our b value constant. We're treating y as a constant. And what we're computing is the derivative with respect to x. So this is a direction parallel to the x-axis. Going back to our vectors, that could be represented by a vector at that point. Remember the vector, the slope of the vector is the derivative. And then similarly, if we hold x constant, or a constant, and we look at the derivative with respect to our y value, it's going to be a direction parallel to the y-axis, or we could look at this in terms of vectors as this vector. That's very limiting. Okay, so it would correspond to some direction on our surface, which is super limiting. Because when we find derivatives, we're finding rates of change. And you think about in a real world application, typically you want to find your maximum rate of change or your minimum rate of change. Something else that may be important is whether there is no rate of change. And these critical values might not happen when we go in directions parallel to the x or the y axis. It may happen for some random direction. I'll call this vector u. So what if the maximum rate of change happens in this direction? Well, you wouldn't be able to find it if all you did was compute the derivative in terms of x or in terms of y. So this brings us to our directional derivative. But before we talk about that, let's go up to the second bullet. A directional derivative gives the rate of change in any direction of a unit vector. The unit vector is some vector in the xy plane. Okay, so theta would be the direction angle for our vector u. Since it's a unit vector, it would be on a unit circle. The head of the vector would be. So we can describe it as cosine theta sine theta. Well, that's a little bit confusing. Let's go ahead and draw, oops, let's not draw a thick line. Let's go ahead and draw a thin line and just look at what we're talking about in the xy plane. So we have some point, we have some vector, I'll write this in red, some vector u at this point AB. Well, if I were to move u to the origin, then theta would be the angle formed between that vector u and the x-axis, which is called the horizontal. Now let's go back to this vector u. If I went ahead and at this point AB drew myself a right triangle and I called the hypotenuse some length h, then I would have sides h cosine of theta, h sine theta. So you can just go ahead and verify that using the Pythagorean theorem. H squared cosine squared theta plus h squared sine squared theta, that should be equal to h squared, which it is. If I factor out the h squared, I just get cosine squared sine squared, which is 1. So this relationship holds. And the reason why I want to look at that is because it brings us to our directional derivative in this box below and its definition. So if you wanted to compute the derivative in any direction, well, first you're going to need to have a direction vector that we call u, and we're going to let u just be a unit vector. To compute the derivative with respect to the direction of this unit vector, we're going to do a capital D sub u. So this notation means directional derivative with respect to the vector u, given our function at some point AB. So we're going back to our limit formula definition for a derivative from Calc 1. As h goes to 0, we end up with f of a plus h cosine theta, b plus h sine theta, minus f of ab over h, which is a horrible formula to use. The limit formula for derivative has always been very tedious. And to add to that, you would need to know your theta value. So what we typically use, and again, this happens a lot in math, is we use another formula that's more usable. And that brings us to theorem 14.10. If you want to compute the directional derivative given any unit vector, and it's important that it's a unit vector, otherwise you'll be scaling off your derivative. Okay? We only need u for its direction, not its length. So we have this unit vector. Then what we can do instead is use a dot product between the two vectors. The first vector is going to be the partial derivative of f, partial derivative of y, and then we'll dot it with our unit vector. So just to let you know that this vector here, this partial derivative with respect to x and y, this is what we call a gradient vector. And we'll talk more about that in a little bit. But let's go ahead and compute a directional derivative given a function. In this case, our function is x squared cosine 4y. We're given a point, 1 comma pi over 4, and we're given a direction vector v. Notice that v may not be a unit vector, so we're going to have to check that first. Now, I typically don't work in IJ because I like to use vectors without those variables I and j. It's just tedious. So the first thing I want to note is that I need a unit vector. So I want to take my vector v, and divide it by its magnitude, which would be 4 plus 9, so square root of 13. And now I have a unit vector in the same direction as v. You can distribute that if you want and write this as 2 square root of 13, negative 3 square root of 13, but it's really not necessary. So to compute my directional derivative with respect to u of my function, I take the vector of the partial derivative with respect to x, which would simply be 2x cosine of 4y, comma, partial derivative with respect to y would be x squared sine of 4y times the derivative of 4y, which would be 4. Oh, but it would be negative. So this is going to be negative 4x squared sine of 4y. And I didn't really go through all the steps. That was in the previous section. So partial with respect to x, partial with respect to y, and then I'm going to dot it with this vector 2 over the square root of 13, negative 3 over the square root of 13. This will simply be a multiply, add, multiply. So 4x cosine of 4y over square root of 13, negative, negative, that's going to be a plus 12x squared sine of 4y over square root of 13. Oops. All right, I'm excuse me. Sorry about that. So I'm not going to combine these because the point in this problem is to compute this directional derivative at the point 1 comma pi over 4. So if I simply put in 1 for x and pi over 4 for y, it looks like we have negative 4 over the square root of 13 plus, if y is pi over 4, sine of 4 times pi over 4 is sine of pi, which is just 0. So the second term is just 0. And that's actually it. This would be my directional derivative. Negative 4 over the square root of 13. So I would like to point out that if you're evaluating the directional derivative at a point, you don't have to go through all of these computations. We could have simply plugged in 1 for x and pi over 4 for y when we had this in vector form. So we would get the vector negative 2, 0, and then we would dot it with the vector 2 square root of 13, negative 3 square root of 13. So really it's only necessary to compute the directional derivative and keep in the variable x, y all the way through if you're not evaluating it at a certain point. So does this end up to be negative 4 over the square root of 13? Yes. So the second term would be 0. The next thing I want to talk about is that gradient vector, the partial derivative with respect to x and with respect to y. This is a very special vector, and it's going to come into play probably in the all the remaining sections. Okay, so something that I would like to bring up is some notation. If we just look at this symbol, and this indicates it's a gradient vector, if we just look at that symbol, it has a definition in its own right, and we call that the del operator. The definition for the del operator is a vector where it's a partial derivative with respect to x, partial derivative with respect to y. So something to note is if I take this del operator and I multiply it by my function, I get the partial derivative with respect to partial derivative of f with respect to x, partial derivative of f with respect to y. So that's just a note that I wanted to clarify. Again, we can shorten this into the vector f of x, f sub y. Let's go ahead and compute our gradient vector in example 2, and then we'll evaluate it at the point -5, 2. Our gradient vector, and here it's nice to put in the variable xy, would be partial with respect to x, 2x minus 2y, partial with respect to y, negative 2x plus 2y. Now if we evaluate our gradient vector at the point -5, 2, we'll still get a vector, and it's going to be the vector -14, +14. And it's as simple as that. Let's do another example. For this example, just remember that the derivative for tangent inverse is 1 over 1 plus the argument squared. So when I compute the gradient vector, I'll get the vector with respect to the variable x. I have cosine of x squared. And then I'm going to multiply it by the derivative of the argument of x squared, so that would be 2x. And then when I compute the derivative with respect to the variable y, I get 1 over 1 plus y squared squared, so y to the 4th, times the derivative of the argument, which would be 2y. I'm going to go ahead and just clean this up. That's a vector 2x cosine x squared, 2y over 1 plus y to the 4th. Next thing I want to do is talk about some properties with our directional derivative and our gradient vector. So here in the notes, the directional derivative is the dot product between two vectors. So if we go back to our previous chapter where we talked about dot products, remember that that would be the product of their magnitude times cosine of theta. And this theta is not the theta of u with respect to the horizontal x-axis. This theta is the theta angle between the two vectors. And I have a typo here. That equal sign should not be there. So since our vector u is a unit vector, its magnitude is 1, we can simply compute the directional derivative by looking at the magnitude of the gradient vector times cosine of theta, if we happen to have theta. The important thing about this is it gives us where our derivative reaches a maximum and a minimum. When you look at the directional derivative, and here we're going to refer back to this final expression, the magnitude of our gradient vector is never going to be negative. It's always going to be some positive value or 0. So the value here is totally dependent on the value of our cosine. If cosine goes between -1 and 1, then this expression is going to reach a maximum value when cosine is equal to +1. Oops. So the directional derivative reaches a maximum value when cosine of theta is +1. So it makes sense that when cosine of theta is -1, we'll have a minimum value. And then if cosine of theta is 0, that means our directional derivative is equal to 0. And when a derivative is 0, we're looking at a constant function. So we have no change in our directional derivative when cosine of theta is equal to 0. But typically that theta would be equal to 0 when cosine of theta is 1. And if the angle between our gradient vector and our unit vector is 0, that means they're going in the same direction. They may have different lengths, but they're going in the same direction. Cosine of theta is equal to -1 at pi, and 0 at theta equal to pi over 2, 3 pi over 2. So these properties bring us to our next theorem, which is a really important theorem because it tells you where you find your minimum, maximum rates of change and where you have no rate of change. So let's say that we have this differentiable function and we're looking at a particular point AB. And here we're assuming that the gradient vector is not the 0 vector. So we're going to have the maximum rate of increase in the direction of the gradient vector. The rate of increase is simply the magnitude of that gradient vector. So we have a maximum rate of decrease when you take the opposite of the gradient vector, or it's negative. And then the rate of change would be negative magnitude of the gradient vector. Now in property 3, the directional derivative is 0 in any direction that's orthogonal to the gradient vector. Which brings us to example 4. We have this function x e to the y, and we need to find the rate of change at the point 3, 0, 3 in the direction of the vector -2, 1. And I'll ignore parts B, C, and D for now. Let's look at part A. We're trying to find a rate of change, and we're given a direction. So that tells me that I'm trying to find a directional derivative. Now the direction vector I was given is just some random vector v. I don't know if it's a unit vector. Notice that the point here is 3 coordinates x, y, and z. And that's because the number that we find is going to be the rate of change on the surface of my z function, which is why we're given 3 coordinates. However, we only need x and y to compute the value. So let's start with A and then we'll go to the rest of the parts of this problem. I need to find the directional derivative, so I need my gradient vector. When I compute that, the partial with respect to x is e to the y. Partial with respect to y is x e to the y. And I'm evaluating this at the point 3, 0, 3, but I'm only concerned with the x and the y value, so 3, 0. And that would be 1, 3. I have my gradient vector. I need my unit vector. So I'm going to take the vector I was given, -2, 1, and I'm going to divide it by its magnitude, which would be the square root of 5. My directional derivative, evaluated at the point 3, 0, is simply the vector 1, 3, dotted with, I'm going to bring out the 1 square root of 5 and kind of ignore that. So I'm just going to dot the vectors and I'll multiply it by the 1 over the square root of 5 later. So it looks like it's going to be -2 plus +3, which is just 1. This is simply equal to 1 over the square root of 5. And that's what we were asked to find in part A, the rate of change at that point on the surface of my z function in that particular direction. So it's 1 over the square root of 5. Let's move on to part B. Part B says, in what direction does f have the maximum rate of change? Well, we're just going to use our previous theorem. The maximum rate of change occurs in the direction of our gradient vector. So what is the maximum rate of change? Is its magnitude. So if we look at the gradient vector evaluated at the point 3, 0, that was the vector 1, 3. That's the direction of maximum increase. So this is, I'll just put max increase. So this answers the first part of that question. And then when we look at its magnitude, which would be the square root of 1 plus 9, so the square root of 10, this is the max rate of increase. C is asking for the minimum. So I just take the negative of my gradient vector, which would be the vector -1, -3. That would be the direction of max decrease. And its magnitude, or the negative of the magnitude of our gradient vector, would be negative square root of 10. And that would be the max rate of decrease. Part D. In what direction, if any, does the function remain constant? Oh, this is fun. So it's going to be constant when the gradient vector dotted with our u vector, not the one that was given though. This question is asking us to find a vector u, if it exists. It's not the same vector that we were given. The point is the same, the function's the same, but we're trying to find a vector which gives us no rate of change. So we need to find this vector u so that when we dot it with the gradient vector, we get 0 because they have to be orthogonal by the third property in our previous theorem. I know my gradient vector. The function's the same, the point is the same, so I know my gradient vector is still going to be the vector 1, 3. I just have to dot it with this u vector, which I'll call u sub 1, u sub 2 for the components. If I compute this dot product, I get u sub 1 plus 3 times u sub 2 is equal to 0. So sometimes you get lucky and the equation that you get when you do the dot product is solvable, but this one's not. I don't get a unique solution because I have two variables in one equation. So at this point, I just have to think about this critically. All I have to do is find one vector that is orthogonal to my gradient vector 1, 3. And if I look at this equation, if u sub 1 is 3 and u sub 2 is, say, -1, now this is not unique, then if I dot it with my gradient vector, I get 0. So if this particular vector gives me 0, then any scalar multiple will also give me 0 when dotted with my gradient vector. So actually my vector u is going to look like this. where c is just any constant. And you could try it out. Just pick different c values, dot it with the gradient vector, you'll get 0. So that vector would be the direction where the function remains constant. We're going to move on and look at applications of this gradient vector. It is very powerful. And we're going to review in Theorem 14.12 level curves. So remember what a level curve of a surface is. You're just intersecting the surface with some z-plane. You'll get a curve that you will push down to the xy plane. It so happens that, and we're going to look at some properties, that our gradient vector will give us an alternate equation for a tangent line. Let's look at this diagram. Let's say we have this level curve, so that would be the green curve. The property of a tangent vector, here that would be this curve in pink, and the gradient vector at any point of a level curve is that they're going to be orthogonal. So you pick any point on your level curve, and you look at your tangent vector, and you look at your gradient vector, and they will always be orthogonal. And that's really important. I did want to make a note though. Notice that this tangent vector is a lowercase t. That's because this is just any tangent vector. It is not the unit tangent vector. So this is not capital T, which is our unit tangent vector. It's just any tangent vector. So if you take any tangent vector on your level curve, it's always going to be orthogonal to the gradient vector. So another property that comes up is with Theorem 14.9. So remember, that's when we did implicit differentiation. And we found the derivative of y with respect to x, which was simply negative partial with respect to x over partial with respect to y. Well, remember, that's a derivative. A derivative is a slope of a tangent line. So our tangent line is going to have derivative, or is going to have a slope of negative partial with respect to x divided by partial with respect to y. And we'll be putting all this together pretty soon. Something to note, that any vector pointing in the same direction of the tangent line at this point AB will be a scalar multiple of our tangent vector. Why is the tangent vector defined as negative partial with respect to y, comma partial with respect to x? Well, let's just verify that. If you take this vector, negative partial with respect to y, partial with respect to x, and you dot it with our gradient vector, which is partial with respect to x, partial with respect to y, the dot product's 0. And if you take any point on the tangent line, any point xy, create the vector x minus a, y minus b, you dot it with the gradient vector, they're also orthogonal, and that dot product will be 0. So this finally brings us to the tangent line, to our curve. And remember, it's a level curve. The z naught does not represent the value when z is equal to 0. Z naught is just any constant c that we substitute into our z equation. So if you have a level curve To find the equation of a tangent line at any point on your level curve, you use the following last equation. And it comes from that second to the last bullet point that we just looked at. If we compute that dot product, then we get the equation of our tangent line. So it's a partial derivative with respect to x evaluated at the point AB times x minus a plus partial derivative with respect to y evaluated at the point AB times y minus b equal to 0. Okay, so let's go ahead and in example 5, we're looking at this paraboloid, 16 minus x squared over 4 minus y squared over 16. So that's equal to our z. And we're going to look at the point 0, comma 16. On this specific level curve, f of xy equal to 0. So all that means is that we're going to replace our z value with 0, and this is the level curve. This is the equation that we're going to be looking at. We're going to compute the slope of the tangent line at the point 0, 16. Notice that if I do put in 0 for x and 16 for y in this level curve equation, it is equal to 0. So this point 0, 16 is a point on my level curve. And then we're going to verify that our tangent line is orthogonal to the gradient at that point. So let's first compute the slope of our tangent line at the point 0, 16. We're going to use that the slope dy dx is equal to negative partial with respect to x over partial with respect to y, which means my derivative is going to be a negative. The partial with respect to x would be negative 2x over 4 or negative x over 2. I'll put that in parentheses. The partial with respect to y, negative 2y over 16, so negative y over 8. Oops. And that simplifies to negative 4x over y. I want to evaluate this derivative at that point 0, 16. So when I put in 0 for x and 16 for y, I simply get 0. So the slope is 0 at the point 0, 16. The next part of the question says to verify that the tangent line is orthogonal to the gradient at that point. Because we're talking about the tangent line. Now, if we look at this last bullet, it gives us the equation of the tangent line. But notice that it's not in vector form. If I'm verifying that the tangent line is orthogonal to the gradient vector, then I need to write my tangent line in terms of a vector. And this is very easy to do. All we do is look at the tangent vector equation, which is the negative partial with respect to y, partial with respect to x. So that's what I'm going to use because I have to verify orthogonal. I'm not going to look at that bottom equation. If I compute that tangent vector, I'm looking at the negative partial with respect to y, which turns out to be y over 8. Partial with respect to x is negative x over 2. So at that point, 0, 16, this vector is simply 2, 0, right? Because x is 0, y is 16. If I take this vector and I dot it with my gradient vector, so remember our gradient vector is negative x over 2, negative y over 8, but I'm evaluating this gradient vector at the point 0, 16, which gives me the vector 0, negative 2. So I can see that when I dot product these two vectors, oops, helps if I put a t, and the order really doesn't matter. That gives me 0. So I've just verified that the tangent line is orthogonal to the gradient at that point. So whenever you're working with tangent lines on level curves, you can either use that bottom equation if you just need the equation of a tangent line, or you can use the vector form if you need to dot it and show orthogonal. The last concept that we're going to talk about in this section is computing directional derivatives for higher order functions. So imagine if we had some function of 3 variables, x, y, z. Then the gradient vector is simply the partial with respect to x, y, and z. And the directional derivative is simply the dot product of our gradient vector with our unit vector u, which is a u sub 1, u sub 2, u sub 3. And you could probably guess that we can compute our directional derivatives in even higher dimension space, functions of 4 variables or 5 variables. As long as there's a finite number of variables, we can compute the gradient vector and the directional derivative. Let's look at example 6. We want to find the derivative of our function, sine of xz plus natural log of 2y plus z, at the point pi over 2, 0, 1, and the direction is going to be this v vector 1, 1, 2. So since we're finding a derivative and we're given a direction, that means we're going to find a directional derivative. I'll need my gradient in terms of x, y, and z. The partial with respect to x. Notice the natural log of 2y plus z has no x value, so the derivative there is simply 0. So the derivative of sine of xz in terms of x would be cosine of xz times the derivative of the argument with respect to x, so that's just z. This ends up being z cosine of xz. The partial derivative with respect to y, so the sine of xz, that's derivative of that is 0 because there's no y value. So we're just looking at the natural log of 2y plus z, which would be 1 over the argument times the derivative of the argument. And that ends up being 2 over 2y plus z. The last term is with respect to z, unfortunately, sine of xz, natural log of 2y plus z, they both have z values in it. So if we look at sine of xz and we take the partial derivative with respect to z, it's going to be cosine of xz times x, which would be x cosine of xz, plus 1 over 2y plus z times the argument, and that's just 1. This would be plus 1 over 2y plus z. Now I evaluate my gradient at pi over 2, 0, 1, and that looks like it should be 0, 2, 1. I need my unit vector, which is simply my vector v1, comma 1, comma 2, divided by its magnitude would be the square root of 6. So now the derivative at pi over 201 is the dot product of these two vectors. And I'll just keep the square root of 6 in the denominator and kind of ignore it. Do the dot product of these vectors. That should be 2 plus 2, 4. And divided by the square root of 6. And that's it. At the very bottom box, there's some properties that you may come across. And they're properties with gradient vectors. If you have a constant times your function, and then you find the gradient, you can also factor that constant out, compute the gradient of your function, and then multiply by that constant. So if you're taking the gradient and you're adding or subtracting two functions, you can always distribute that del operator and take the gradient of f plus or minus the gradient of g. An interesting property with gradient is the product of two functions. If you take the product of two functions and then you find the gradient, it's actually the product rule from calculus. So you can keep f gradient g plus keep g gradient of f. So when you're dividing functions, it's simply the quotient rule. And that's it for this section.